right, good afternoon. So I've got your exams. I'm going to give people a couple more minutes to filter in before I start handing them back. But just a few quick words about it. As I don't know, have you guys bothered to go back and look at the exam solutions, or are you just waiting until you got the actual exams? Just waiting. Okay. I haven't downloaded that from Twitch yet. It still should be up there. I think it got another little bit of time. So I'm going to do that probably tomorrow. But if you wanted to see it, it's there. When you watch it, I comment on some of the problems. So I'll just briefly touch on it right now. I know that a lot of you, probably everybody, was feeling on that second problem with the parts per million that like, oh shoot, this looks so easy. Why am I blanking? That, imagine that was on everybody's mind. And I realized that, technically you had the information and we had talked about it and we'd done problems similar, but we hadn't really done that type of conversion and forced you to go through that process specifically. And so I did have some sympathy. I tried to be a little bit lenient if you had a good bit of the process there. And if you go back and watch, essentially what you had to recognize was ppm is just like percent, right? pph would be parts per 100%. And with that, you can use your knowledge with the ideal gas law to say, well, some fraction of this gas based on that percentage, but it's times 10 to the minus 6 instead of times 10 to the minus 2, which would be a percent per 100. To just take it that much further and say, okay, well, only 0.000000008 of this volume is this gas. And then you could take that, and since the ideal gas law relates moles to volume, you can then find the number of moles of that gas in that cubic meter and solve for the micrograms. So that was the approach. And again, it sounds simple once I say it. Nobody got it right. Okay, nobody got the problem right all the way. So varying levels of credit. Obviously, partial credit was awarded. I have sympathy at the same time. I was hoping that some people would get it right. So maybe that's on me. Some of you did have a better grasp of what you're supposed to do. So I recognized a lot of you were thinking well about it. So I was happy about that. You see the exam distribution here. Again, I intended for this to be easier and shorter. Technically, it was not a long exam compared to some, but I knew a lot of you had 2 exams, so I felt bad that there was 2 sort of curveballs. That the other one was problem 3 was trickier than I realized when I put it there. I had done the problem before, and when I saw it, I was like, oh yeah, it's the washing machine thing. Well, it's a batch reactor, it should be simple. But the complication there is you have to track the mass on the clothes itself, not in the water. So I regretted as well that. So overall, I think you did pretty well given all of that. Understandable that the average was 75, perhaps a little lower than I meant to have there.
What's that ST? Is that standard deviation?
That's a standard deviation, yeah.
What does that mean?
So standard deviation is kind of it's a measure of how variable the average is. So if you have some average, let me put this on real quick.
You don't have to.
It's basically a measure of the width of the distribution.
Oh, okay.
In a sense. So if you had a very sharp point somewhere, that would be very small standard deviation.
Okay.
So in some sense, it helps me if it's just an analysis there. Yeah. So anyway, this is the distribution. You can see that how many people scored within A, B, C, or whatever based on the bin categories. That doesn't mean 3 people got 100. That means 3 people got between a 90 and a 100, basically. That's the way to read that histogram. I'll show you in a minute as well how I did this in Excel with some fictitious data for you as a little Excel blurb, I guess. Our plan for today, I'm going to pass these out, includes your homework assignments as well. So I'll pass these back for all of you that are here. If you're not here today, then I'll try to be bringing them to class in the future. Thursday, I thought we were going to be in person, just canceled fall break, and then we'd be in person to make up the class. Turns out their intention was for us to cancel fall break and then do virtual class. So I got an email earlier, it's like, okay, I will be at my actual house this time, and hopefully there won't be a Comcast truck at the front of the neighborhood doing repair work on the line as I'm trying to teach. That literally happened. My first class was interrupted partway through. The internet just shut down for the entire neighborhood. So it came back on briefly later, and I was like, okay, maybe we'll have class, and then it went off again. So that was Thursday. I'm sure you guys didn't mind too much. Sorry about that. But there you have it. Okay, so and then eventually we'll get to some chemistry today. I have a couple more comments about the homeworks and stuff, just somewhat helpful hints, I hope. So I'm going to read out names. Let me know if you're here. I'm trying to learn names. I definitely don't have everybody, and it's difficult with the masks. So bear with me, and I'm not native to Louisiana, so if you have a Louisiana name and I butcher it, just politely make fun of me and let me know how to say it properly. Okay, Sarah Andre? Madeline England? It's going to take me a moment because I have the homeworks with each one. Kelsey Batten? Mason Bailey? I see 10 people online, so see how many people we get. Michael Barden? Abigail Bolander? Sort of alphabetized them approximately. Tucker Brown? Emma Champagne? Eva Counts? Caroline Harrison? Maddie Hathcock? Brandon Hewitt? Francesca Hunt? Ann Jones? Abby Mitchell? Alexander McDonald? Derek LeBlanc? Cameron Kimber? Lauren Petrie? Jordan Post? Jordan Radford? Landon Reed? Rashad Richard? Clayton Rives? Alyssa Samuel? Mason Felix? Lauren Solo? What was it? Thank you. Piper Smith? Sydney Smith? Emma Steiner? Ruth Van Overberg? Aaron Walsh? Madeline Boutin? All right. So I'll make sure that we have the YouTube link posted online for that tonight or tomorrow. You can also go to the Twitch page. It should still be there. If it's not there, I'm going to have to re-record it, which would not be great, but I would do so if I have to. Okay. So we talked just briefly about the distribution here. I do want to show you real quick how I did that, because I think this is a useful tool in Excel. I'm trying to highlight useful Excel tools for you. So in Excel, we can take some set of grades, and this is just, I took some grades from some previous semester and changed a bunch of them, and so I have them basically here all anonymized and not even real grades necessarily. What I did was I wanted to take all of these grades, 80 students or whatever, and sort them into how many fell within 89 to 100 range between those numbers in that bin, 79 and 89, 69, 79, and so on. And then report that. And so Excel will do that for you and count the frequency, how many times a number falls in that range. So classic histogram here. And the way it works is you set up a bin category and you have your data, and then you tell Excel to do the work. If you don't have the data analysis pack added in, you have to go through, like I showed you that other time, go to the options, go to add-ins, and click add it into it, because it's not usually there by default. So anyway, once you have it there, you can go to data analysis. And if you do ever have a question about that, I'm happy to help. It brings up this little box that's hard to read because it's so small. There's one called histogram, and that'll bring up another box. And we have an input range. So I'm going to put in the input range, that's going to be my data that's going into the analysis. And then I have a bin range, which will be the set of bins that I set up. And I essentially just highlight those ranges. Yeah.
What was the keyboard shortcut you just used to highlight all the
Good question. For keyboard shortcuts, let me finish this and then I'll say that. So this will give you a chart output. It can add labels. I like to put it in a specific spot in my current workbook, and that's what I did in the past. I'm going to put it right here because, I'm going to tell it right here. It'll put the bin and frequency setup right there. and then I also want it to do a chart output, and it should do it in this workbook. So once I've got all that, hopefully this will work. It tells me, well, you've got data there. You sure you want to overwrite it? And yes, I'm fine with that. And it says some of this data is technically hidden in the charts. So then, boom, we get a histogram. I can label that however I like, and fuss with it. Do all those things I might want. And you can see it gave us this this histogram where we had how many were between these numbers and all that good stuff. I feel like it did something a little funny. This shouldn't say 100, I don't think. Maybe I was supposed to grab the bins when I did that. So I'm just going to redo that real fast. See if that fixes it. So it's very handy if you ever need to do some analysis like this. Definitely recommend it. Excel has tons of things that you can use. And I'm just going to select all that. There we go. Okay, so that's how I was expecting it to look. All right, so a couple quick tips here for navigating Excel, especially when you're on a touchpad. If you're using the arrow keys up and down, left, right, that's kind of handy. If you hold Control and hit down, it's going to bring you down to the next time there's a gap. So if I do it again, it's going to bring me down to the very far end of Oblivion in Excel. And then when I press Control up, it brings me back to the next data point found. So if I hit up again, it's going to bring me to the top where that's the last cell in the range. So that's handy just for navigating, Control and then moving left, right, up, down. And then if you do Control Shift, because you can do, let me just do Shift first. If you do a Shift, it's going to highlight multiple ones. I'm holding Shift and I'm pressing the buttons, right? The directional buttons. If you do Control and Shift and hit down, it's going to select all that. And I can go right and hit that column, and then when I go down now, it should go to the bottom of that column. Oh, no, just kidding. It went to the very bottom because that was the next one in line for the column I started in, I guess.
What's the farthest, like, it goes from A to Z, what's after Z?
XFD. It goes AA, AB, AC, all that, and keeps going through the alphabet. And maybe a good math problem to figure out how many exactly that is, but yeah. So it's pretty handy. Another thing you can do is you can do Shift End, and that should go to the right, I think. Oops, hang on. Oh, that was page up. Shift End, no, that didn't do anything. Control End goes to somewhere. Okay, Control End went to the right, and I'm not sure. I guess there was some marking here, so that maybe that was what it's catching. You might be able to use Home and End a little bit too, but I like the arrow keys, just Control Shift, all that. When you're doing that, if you had some sort of equation, let's say equals this minus 1, and you wanted to repeat that pattern down, Control D will fill down and repeat that. I'll basically copy paste that all the way through. You can also use that to the right. So Control R fills it into the right. So just a few things. If you need a quick formatting, Control 1 pops you up to the format cells. So if you needed to superscript something, it's a quick way to do it. Or subscript. So okay, so that's the Excel lesson for today. Try to give you a reason to practice this kind of stuff later. I was thinking also in terms of the homework, and this kind of brings us to the next slide. For the homework, I might give a competition next time I give some sort of Excel thing to see who can make the most visually appealing figure for me, and award extra points for that to make it a bit of a competition for you. So I just wanted to make a couple quick notes on to encourage you to practice professionalism as you're doing homeworks and stuff. college is nice because you don't have to worry so much about this kind of thing, but it is a good time to start working on it and start building habits. I'm not like fussed about the homeworks or anything, but certain things stand out as kind of noticeable. If it takes me a lot longer on some papers to find the actual answer than others, that could accidentally build frustration in me. And, you know, I would hope that doesn't affect my grading at all, but who knows if that would affect somebody. And in a workplace later, that may affect people's inclination to work with you or something, right? So just to, you know, I do my best to not let that affect me and just grade based on the work. But if it does look like whatever this is, maybe I can't see it at all, right? So just be cognizant of that. If you turn in work without staples, that's, you know, try to get a habit of being prepared in that manner. You know, maybe it would be nice if I had something here, but if everybody did that, then I'm buying staples every so often, right? And that's not quite a great expectation for you to have of me, although maybe that was fair in you know, grade school or something. But that things like that, it might be worth the extra 5% effort to polish something, and you might benefit from thinking this as if you're in a workplace and giving a colleague something like, hey Sam, here's something, here's a report, can you take a look at this for me? Or, you know, I completed this for the task that we're working on. That kind of approach might help you because, you know, it's something that you want to communicate well with what you're doing, right? So put a little effort in, or I'd encourage you to, and that will probably help. Something on the homeworks, I saw a lot of people show me the Excel, either drawing out the figure, you had done the work in Excel and you drew out the figure. When I asked for a printout, I wanted something to show me that you were in fact using Excel and learning that. So I was hoping for a printout so I could maybe give you a little feedback. At the same time, a lot of cases, you didn't show me the actual work that went into getting it, right? Sometimes not even the data. So it's just like a figure, either drawn or pasted. And so I'm just reminding you that what I'm interested in is seeing you work through the process. There was some background derivations that were required for that problem when it shifted from the steady state to the non-steady state, at least to draw out how you were going to perform the calculations in Excel. So maybe put a table with the data, you know, having the axes labeled is important. So you may have had some points off just to show you, hey, you're not meeting my expectations, even though you did the problem presumably correct. Sometimes I couldn't even tell if it was correct if it wasn't labeled properly. So anyway, not a big deal. None of this is a big deal. Just encouraging you to use the Excel problems. You need to communicate with them. And if you have, once you get to lab reports, whatever classes you have lab reports, you probably will agonize over Excel. If it's anything like my experience with lab reports, it took a very long time, but at the end of the day, you were communicating your process through Excel. It just took some extra effort to do all that and list it all out there. I think it's a good skill to learn, so I'd encourage you to practice using Excel for communication, not just calculation. You'll benefit from that as you make comments to yourself, noting what you've done, whether that's in the workplace, doing research, whatever your future holds. That's going to be a nice skill to have as a habit. Okay. Last couple little things. If you're turning in something online, you know, you weren't able to turn it in person, or if you're printing something, I'd encourage you to take a little care for what your PDFs look like. And first of all, I do ask in my instructions for online submissions to have PDFs. I haven't made a big deal of it. It's no big deal. But I do expect one PDF document with pages that are not, I don't have to do this to read them, you know, that, you know, or to fuss with it, to rotate it in the document and then rotate back when I want to put the grade on it. So again, a little extra effort is going to be stepping up your professionalism and the quality of your work. And it doesn't take a whole lot. Here's a tool that I use, free online PDF editor, because, you know, I think my Office desktop has an official Adobe, so I can edit that one, but oftentimes I'm working from home and I don't have that. And so what you can do with this this website is you can take any old PDF and probably some other things as well. This is just a research article. You can load it in there, and then you can edit it and re-download it. So I'm just going to show that real quick. Maybe. There are other websites, and this one seems to be it's a big paper, so maybe it's a little slow. Okay, so this one, like I said, I uploaded this scientific journal article, and if I decided, you know, I wanted to work with one of these pages and change it, you know, maybe I need to rotate that one because I scanned it funny. Well, there you go. That didn't take very long, and now I can go and use the little download button and download a new copy, having changed the page. So don't make me do that part if I'm the one grading your work, or if you're turning in a task to your colleague, you don't want to send them, you know, junk that they have to like fuss with all over the place to get it readable. So just encouraging you to do that. Another good tool is Office Lens. It's an app for phones. It'll allow you to scan whiteboards. It'll allow you to scan documents as if it's a scanner, and it does some arranging with it and create a PDF. You can create one PDF of all your work instead of sending me JPEGs that are, you know, poorly lit and, you know, just kind of awkwardly arranged or something. Maybe worth a few more minutes of effort. Okay, and with that, I want to get back to chemistry and the topic for today. Any questions or issues so far? Okay. So I don't know how helpful that was, but hopefully that was helpful and not, I don't mean it condescending or anything. I wasn't offended by your work or anything, just some practical tips, I hope. So significant figures, you probably were annoyed with them back in high school chemistry. I'm bringing them up now. I don't think our students get this very often. I think it's good to be a good practice to have. I don't always design my problems appropriately to actually use significant figures, so I'm not saying that it always is a must, but in chemistry and in analytical fields, it's good. It's good to pay attention to because you'll often be reading an instrument that has some precision, and you don't want to lie with your numbers, pretending you know with more certainty than you actually could possibly have, right? So it's a matter of, it's important, especially in the scientific disciplines, to report your uncertainty, because really all science is discovering and reporting how uncertain about something are we. We're not very uncertain that this hypothesis, it's not a good way to say it. We have very little uncertainty for this hypothesis. Therefore, we believe it to be true. It's functionally true as far as we can tell. So with that, perhaps in an engineering problem where we say 10 meters long by 10 meters wide, we don't really care because we're assuming the metrics will be accurate enough to not bother with it. And then maybe a decimal place or two would be fitting for an answer. But if it's something more along the lines of chemistry and there are, you know, some precise digits reported, maybe we have some instrument here that has, you know, a readout that goes to X number of digits. Well, it's important to remember and how to use and process significant figures so that at the minimum, you're not going from a readout that has 4 significant figures and giving me 10 significant figures because you wrote out every decimal place in pi, right? So just a quick reminder how they work. If you have numbers at the front here, those 2 are significant, and then the 2 behind it are not significant because it could be that you rounded those 2. In fact, that's sort of the assumption that if they're just 0 past a couple numbers, unless it's past a decimal place, you know, if the decimal place is here and there's nothing else, these 2 are not significant digits. If you had a dot, you know, if you had your decimal place here, then what we're essentially saying is we have precision out to this decimal place, and so all of those digits are significant. So this is from Wikipedia. It's highlighting in blue the ones that are significant as written. So in this case, 2 for this one, 2 for this one. And this guy, it has that repeating, I think. And I don't really know what it's talking about. I guess maybe that's repeating. I would just ignore that one because I don't know what it's meaning. This one down here, this 3020.40, all of that's significant even though we have got the zeros because it's showing this precision out all the way to here. So that's 6 significant figures. Likewise, this 8002, all of that's significant because, again, it's showing how far we have that precision. You can do this with scientific notation. You could say 8.002 times 10 to the third. Again, that distance past that decimal place, all of that is showing precision there. If you had 7.30 times 10 to the third, the same number as this, except we put 0.30 showing that we have precision in that number. So that's actually 3 significant figures, whereas up here it's 2, even though it's the same amount, right? So it's all about how much precision are we conveying, and what you can imagine is that's coming from how precise our instrumentation is. So you won't always use it, won't always be appropriate for engineering, but if we're using analytical devices, it turns out that we are limited based on how precise they can be. So that is important, and when in doubt, it's not a bad thing to use significant figures. And if it looks like it's a silly thing that you're doing to use them, just make a comment based on this. I assumed significant figures here. That's another tip, by the way, for your exams and homeworks. It's good to show me, even if you've got a wrong assumption, tell me your assumption, because then I can see what you're thinking about, and I know a little bit more about how much you know, which is what I'm aiming to grade you on, is how much you know, right? So if you can help convince me of how much you know, that's helpful. Okay, so back to the very basics of chemistry. I'm just going to go through it pretty quick. All of you should have a grasp on this, but I just want to be sure and be a little bit thorough here. We'll get into equilibrium reactions in a minute, but I want to just practice some of the basics so that we can be building on it and be more comfortable moving forward. We've already done a little bit here and there that I've kind of assumed you're capable of. Okay, so our atomic, or a periodic table, we've got an atomic number. That's how many protons are in an atom. We've got the atomic mass. That's essentially the average weight of oxygen in the Earth system. If we were looking at outside the Earth system, maybe this will change a little if there's difference in the isotopes. So essentially, if this is the number of protons, and each proton is 1 atomic mass unit, AMU, I'll write that in a different spot so it's clear. So 1 proton is 1 atomic mass unit. So essentially hydrogen is 1 proton. Well, every 1 neutron is also. And the neutrons can be variable, right? That's where we get isotopic chemistry. That's where we have the role of radioactivity is often splitting neutrons off. Sometimes other things involved as well. But so that means that this then is essentially the sum of protons plus neutrons. We can kind of ignore electrons. They're like three digits out, sort of a rounding error in most cases. The periodic table does include them, but for the moment, we'll pretend they're not making a meaningful impact. So this is the sum of the protons and neutrons, but on average. So this is the average amount of neutrons would be 8. So we'd have 8 protons and 8 neutrons on average for oxygen, but there are some oxygen molecules or atoms that have 7 or 9 or some isotope that's different than that, right? So that's O with 8 neutrons is the average. An oxygen with 7 neutrons would be an isotope. I'm not sure if that one ever happens realistically. There's sort of some frequent isotopes, right? Carbon-16, carbon-13 type of thing. You've probably heard of carbon-13 dating. Carbon is normally 12. Add an extra neutron. You can use that to track, maybe for some environmental system, how much uptake is this organism, how much of this carbon that we've put in there and on purpose that's actually heavier carbon, how much is it processing compared to other stuff. So this would be just an isotope. Okay, so hopefully all that's familiar. That stuff doesn't really matter so much. I was just wanting to give a little context about where that number is coming from. We use these to get our molecular weights, right? So speaking of oxygen, if we have atomic oxygen, that's just 16 grams per mole, because we're getting that from right here. Molecular oxygen we'll talk about, or if a problem says oxygen in the context of like there's air, then you want to assume that's O2, right? That's the oxygen we breathe. It's not actually O, it's O2. So oxygen, again, should be, hopefully we just review, that's 32 grams per mole, and then ozone is O3, 48 grams per mole. Okay, next would be ions, and we could have atomic ions. So an ion is just an atom or a molecule with a charge in water. I suppose you could have ions in an atmospheric condition, but then that's, I think, called a plasma. So in water, we'll talk about ions in terms of anything really with a plus or minus charge. It could be +2, +3, -1, -2, -3. And then we have polyatomic ions or molecular ions. A few common ones are listed here. I recommend you familiarize yourself. If you haven't seen them in a while, you probably saw them in Gen Chem at some point. But you should be able to recognize, oh, phosphate, that's PO4 with some charge, and as you learn and as you do more chemistry, phosphoric acid is a very common thing to use. It's a handy buffer, used quite frequently in labs. And so what you'll notice is if you add a hydrogen to this PO4 3-, then you get HPO4 2-, and you could add 2 or even 3 to get H3PO4, which is not an ion. So I'm lying there, but you get the picture. This is a polyatomic ion with acid-base chemistry here, with equilibrium reactions that we'll talk about. Same thing's true for sulfate and the carbonate system. There are other ions, nitrate, nitrite, hypochlorite here. This is the, essentially bleach is the HOCl/OCl- pairing. So there's lots of ions. The ones I'm listing here are particularly common in environmental systems. You should probably know these. You will eventually know these just by dealing with problems with them. So if these are super unfamiliar to you, take a little bit of effort to look over them, familiarize yourself with them. Don't be scared of them, right? Probably in Gen Chem you're required to figure out based on the orbitals or the electron pairings, what charge you're going to end up getting. Not too interested in that aspect of it. I'm sure that's a good exercise, but be familiar. The nitrate and nitrite are a good example, ones to be familiar with, involved with almost any water system. You're going to have some of those as nutrients. So be familiar with those. I would probably include ammonia and ammonium ions there, NH3 and NH4+. Those are, so all told, those are pretty much the nitrogen sources of nutrients in environmental systems. There's organic nitrogen too, but that's just organic molecules with lots of nitrogen in them. Okay, so quick refresher on stoichiometry. Really what we're talking about is another mass balance, in this case on the number of molecules or number of atoms. Okay, so that if you never liked this stuff in chemistry in the first place, might be nice to just take a step back and look at it in terms of a materials balance perspective, right? The stoichiometry is just simply making sure we have the same number of stuff. We're not creating or destroying any atoms, not doing nuclear reactions, physics, or anything to break apart atoms. We're just doing chemistry, simple chemistry, and essentially we have that number ratio of reactants and products, and we want to know if we react this number of molecules or moles of something, how many are we getting on the other side? So a simple example would be methane combustion. So if you're feeling confident, go ahead and take a crack at this, balance that equation. We've got CH4, some amount of CH4 plus some amount of oxygen is going to some amount of CO2, some amount of H2O. I'll explain it in a moment, but just get your gears turning to make sure you're tracking with me. It may just be simple stupid that you've done so many times by now, but just in case. I'd like for everybody to get to that point. Okay, so hopefully you had a chance at least to scratch your head and think about it. So what I'm going to do is say we'll start with the carbons. If we take a look at the molecules here, we have a carbon in the methane and a carbon in the CO2. There are no other carbons, so one on each side. That's kind of handy. So I'm just going to go ahead and set those as 1 because one carbon should match one carbon. Even if we decide to increase those numbers, they're going to be equivalent because we can't get around the fact that one carbon will relate to one carbon, right? So after that, we have hydrogens also in just 2 spots, so we'll go ahead with those. We have 4 over here, 2 per water molecule over here, so we're going to need 2 water molecules so that we have 4 hydrogens on each side, right? So then what's left is oxygen, and on the right, we know we have, according to our setup so far, 2 here and another 2 here. So we need a total of 4 on the left side. That means we need 2 O2 molecules, right? So pretty straightforward. Watch that process though. Some might be slightly trickier, but if you go by that process of, okay, I'm going to start with one thing and make sure that it's equal on both sides, and then start with the next simplest item, make sure that's equal on both sides, then you should be pretty good to go. I expect you to be able to do this on random problems. So if this is any source of struggle or hang up, let's chat. Let's make sure you have more practice on it. I think we might do a little bit here in a moment. So an example would be if we took 100 grams of butane, how much CO2 mass would we produce if the butane is fully oxidized? And by fully oxidized, I mean converting completely to CO2. So by this reaction, we have butane plus oxygen, burning it, presumably, going to some amount of CO2 and some amount of water. And so here we're adding in the component that we start with some mass of butane, and we want to know the mass of CO2. So go ahead and give that a shot for a minute. You'll see that you need that stoichiometry in place in order to solve the problem. Okay, so in balancing the equation, I'll let you finish the calculations in a moment, but I went ahead and said 1 butane, that's going to be 4 CO2s. Then I did hydrogens, that's 10 on the left, so we need 10 on the right. That gives us 5 here. What I want to point out is we could do one of two things because we have an odd number of oxygens now. There's 8, there's 13. We have 8 here and 5 here. Over on the left, we have a fraction to deal with, so we could just leave it as 13 over 2. Some people don't like that. They like to have whole numbers. So if you wanted to do that, you could just multiply everything by 2, and then it would be 2 here, 13, 8, and 10 to make nice happy numbers. Doesn't matter to me, so whichever way you want to go with. I just wanted to, in case there was any issues, point that out. Put the molecular weights up there, so you can go ahead and finish. All right, so one thing you'll notice if even if, regardless of where you are in the problem, one thing you'll end up having to do for these types of problems is really go from the mass that you were given, that mass of butane, convert that to moles, then we use the molar ratio. That's what the stoichiometry gives us, is some relationship between the moles of each molecule. And we'll use that to convert to the moles of the new molecule that we're interested in, and then convert that back to mass of that new molecule. So I think I mentioned at the beginning of this class the importance of calling a mole it's like a dozen eggs, right? You could weigh the mass of one egg versus one chicken egg versus one ostrich egg, or the mass of an egg versus the mass of a car, but the mass isn't always the right comparison, right? It doesn't take 1 ton of eggs to egg a ton of car, right? You can use a few eggs and it works, right? Presumably. So that's going to be the process almost any time. So if you're getting stuck, remember the stoichiometry is really giving you a mole-to-mole comparison so that you can do that stepwise conversion. So let's go ahead and do that real quick. So we were given 100 grams of butane. Just abbreviate it like that. We need to convert that to moles, so we can divide that by our molecular weight of butane, which is 58 grams per mole. This will give us, let's go ahead and grab Excel just to track it. Okay, so we've got 100 divided by 58. This will be moles butane. .72. we can then take that and convert it to moles CO2 by multiplying by the ratio here. We have 4 moles of CO2 for every 1 mole of butane. So that's the step there. If you do have any confusion with these types of problems ever, that's probably your missing step. Understanding how you're converting those processes. So once you've done it a lot, it should be a no-brainer. So 4 moles of CO2, we'll say 4 moles CO2 for every 1 mole of butane, and that'll give us 4 times that. And while we're at it, we might as well, we'll recognize the moles butane will cancel, so we're at moles of CO2. And while we're at it, let's go ahead and multiply, instead of say equals, let's just say we're going that way. We'll multiply by the molecular weight of CO2, 44 grams of CO2 per mole of CO2. And then our moles of CO2 will then cancel, and we'll be left with grams of CO2. And that should solve our problem there. And so mass of CO2 should be, we'll take that times 4 times 44. So 303 grams CO2. Hopefully that's what you guys got, 303. Okay, so I hope that's straightforward. If it's not, hopefully this was good review. And if you still need help, absolutely don't hesitate to ask. I know it might feel silly, but this is fundamental. So make sure you're getting a good handle on that. Okay, so that's just more space. You could try it with other types of chemicals. We did methane and butane today. You could do propane. You could do something more complex and say maybe you have something with nitrogen in it and then you form some nitrous oxide or something. You could complicate it, and maybe we'll encounter some problems that are a little more complicated, but the same principles apply, so just make sure you're comfortable with that. So those are forward type reactions. Combustion, you can't really reverse it directly. You're releasing so much energy from breaking the bonds that's not a type of reaction that you can just simply add some energy or something to it and send it back the other way, back into butane. You're stuck with CO2. You have to add in a whole lot of chemistry and processes to convert that back from that inorganic form back into some sort of organic form of carbon, something like photosynthesis, right? So there are other types of reactions, which we would call reversible, where you can have a reaction that goes one way and just about as easily goes back the other way. And oftentimes that'll depend on solution parameters. pH is a good example. The pH process itself is an equilibrium reaction. Things like chlorination, so with free chlorine here, HOCl, that's in equilibrium with H+, which is acid, and OCl-, the conjugate base of the hypochlorous acid. So this is bleach. We can also call it hypochlorous acid. And so that would be this is hypochlorous, this is hypochlorite. Combination is what we refer to as bleach. And typically in your household bleach, there's going to be some base added to it to make sure that most of it's hypochlorite and it doesn't volatilize and cause problems. However, in water treatment, we're usually aiming for slightly acidic to do HOCl, because that's a better disinfectant. To understand that, we need to know something about how this balance works. What pH is going to give us the right amount of these things. And so what I want to do now is explore what these equilibrium reactions are and how we can manipulate and deal with them. These are going to be similar to the Henry's law stuff. If you notice, we didn't have any of that on the exam. I felt like it would be good to revisit that as part of the chemistry section, even though we kind of used that to talk about gas phase stuff. In terms of that equilibrium, it is a chemical equilibrium when we're talking about the gas into liquid, just as it is an equilibrium when we talk about our bleach molecules dissociating one way or the other, or reacting back and forth. So you can take a look at these types of reactions as HOCl's reacting to form H plus and OCl minus. You could call this a dissociation reaction. If I spelled that right, I don't know. I feel like there might be a missing S. Anyhow, so that would be what we call dissociating, when we have that molecule and that proton hops off and says, okay, I want to be H plus now. You smell bad. And the backward reaction would be H plus and OCl minus forming together to create HOCl. You can imagine if there's a lot of protons, a lot of H plus in the water, it's actually going to drive this reaction that way. Because if you increase the stuff over here on the right side, that pushes the reaction the other way. So we can push or pull the reaction in either direction by manipulating how much H plus is in the system, the pH of the system. In fact, pH is literally talking about exactly that. So I want to talk about that in a moment. These reactions, a lot of times we assume have reached equilibrium by the time we are doing something interesting with the solution. Maybe in some chemistry aspects, chemical systems, you'd be interested in knowing how long it takes to reach equilibrium or where you're at along the way to equilibrium, perhaps with slower reactions. For our case, typically we're just going to say that we are dealing with systems that reach equilibrium pretty quickly after we adjust it and familiarize ourselves with equilibrium reactions in that manner. I'll show you an example. There's a nice YouTube video of that process heading towards equilibrium. And so you'll see that part of it. And then you'll see what that equilibrium looks like, even if there's a greater amount on one side of the equation than the other, the rates at which they're crossing is the same. And that's what we're talking about with equilibrium. It's kind of that steady state concept that once we reach that equilibrium, the rates are the same, not necessarily the amounts. Okay, so we'll pull up that YouTube video. Does a good job summarizing and demonstrating. And pardon me if the sound is not great, I'll work with it. Looks like for those online, I don't have the video audio coming through, so let me fix that real quick. Okay. Test that.
Process. So in any good reaction, when you start the process, everything's a reactant. So we all have all the water over here, and nothing is a product. When you have a reversible reaction, or a reaction that has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So on our very first scoop, if I'm using two identical beakers, if I go in here and scoop, on the very first scoop, all of it is going to be reactant turning into product, and none of the other. However, the very next time I scoop, some of my product is actually going to go back into my reactant side. Now, if I continue to scoop like this and continue to do this, you'll notice how at first the reaction ran really fast. And at first, a lot of water was switching sides, going to the product side. But then it kind of seems to slow down a little bit. And at some point, if I continue to scoop, the amount that I scoop going each direction will become the same. So if I look, I have 250 milliliters here. I only have 200 on this one, so I'm not quite there yet. Okay. So now if I have 250 milliliters here, I have 225, so I'm getting closer. So I'm almost at equilibrium. And here I have 225, 225. So if we look, and again, this is not perfect measurements, but if we look at our volumes there, they're almost identical, which is showing that the amount that's crossing from here to here is equal to the amount going this way. Now the amount in the beakers represents the rate. Okay, so the rate of transfer is the same. From here on out, I can do this for a day, 2 days, 10 days, 10 seconds. It doesn't matter. This is at equilibrium. Okay, so the amount I take from here goes here, the amount I take from here goes here, and that process will never end. So this reaction now is basically over. It doesn't mean it doesn't keep reacting. It just means it's not going to change anymore. So we've reached equilibrium. Okay, so if we go back to the graph on our slide, we would see that this is the first one, or the top one, where the rate flatlines and becomes equal. Okay, now it doesn't mean that we have to have equal amounts. If we look at our tubs, because I was using the same size beaker, the volume level in the tubs are also very similar. So you'd almost get the indication that maybe the amount in each side has to be equal. So it has to be 50% this, 50% that. And that's not necessarily true. If we reset our setup here, and we begin again, but this time, instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as reactant. I'm going to use the little guy for my product side. Okay, so in our very first scoop, again, it's all reactant, no product. Again, I start scooping and I get some product back to reactant. Okay, now you might think there's no way you can get equilibrium here because the big scooper will always outdo the little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam here. Again, we're looking for equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at about 140 milliliters. So if you look, these two volumes, even though they're in different size containers.
Okay, so that's essentially it. And this works because those are first order reactions. It depends on how much is in those buckets, right? There's some fraction of that, and the beakers are a decent example where it can only take a fraction of that based on how deep it can dip into the bucket. So that was the example I wanted to share with you. That's a good depiction of the process going to an equilibrium and why you can have a bunch of stuff on the one side of the products or the reactants and less on the other, but the rate is equal, right? There's different factors that drive the speed at which those two reactions, the forward and the reverse, are going. But once the overall rate of transfer is the same, then you've hit that equilibrium and it's going to be stable there. That's really how a lot of our pH chemistry works. So, how can we describe this mathematically? Well, we can use this an equation that's describing, that takes what we call an equilibrium constant, and that describes the weight of products versus reactants, and the equilibrium constant is in some way acting as like a balance point between the two. So if we have a chemical equation written out like this, where we have lowercase a as the number of moles of chemical A, uppercase A, plus B moles of B, in equilibrium with C moles of C and D moles of D, then the way we can write that, we'll say the KEQ, so the K, uppercase K for the equilibrium, is going to be the products over the reactants, and you'll notice these are in brackets. So come back to that in just a moment. We'll write that as C, the concentration of C, these brackets, C raised to the lowercase c power, times D to the D, all that divided by A to the A, times B to the B. Recognize here that this is multiplying, not adding. So you'll have this formula in your equation sheet. I see students, and maybe this is just only the civil engineers, and we can just rag on them and pretend like they don't like chemistry, because they never do. But a lot of them will make the mistake of using a plus, which is not right. We need to use multiply, right? This is C to the C power times D to the D power, right? It's a multiplication, just wanting to make sure that's clear. People occasionally get confused on that. Now, the brackets here, if you don't remember, this is extraordinarily important. Anytime we have brackets, this is referring to the moles per liter of X. So let me write that a little better. We'll use a different one. We'll say A. So if we have A, that is A moles, moles of A per liter, right? That's the molar concentration of A, moles A per liter. So that's molar concentration, that's molarity. Always, always, always brackets is moles per liter. That's not millimoles per liter, that is moles per liter, okay? So always watch the brackets. If you ever have a problem, you're given some milligrams per liter of some acid or something, you will have to convert that into moles per liter to do any equilibrium chemistry, because we're on a molecular number to number basis, okay? So just want to make that especially clear. That's why these are in brackets. Over here they're in brackets. Now this reaction is pretty much, that's just pretty straightforward there. If you have some amount of products, this K is essentially telling you where is that relationship going to be. Is it 50-50? Is it 80-20? That KEQ describes that ratio. Now, a lot of times this will have an H plus in it. So for example, if we take the reaction of water, which is an equilibrium with H plus and OH minus. If you're not familiar, that's the acid-base chemistry of water here. That's where we can get H plus in water. The KEQ here for water, I'll call it KW, is equal to 10 to the minus 14. And that's going to tell us something about how much of water is in the form of these ionic species. So it turns out, so if we say that then is equal to the products of that reaction, so H plus, and this would be raised to the 1 power because we have 1 here. Turns out a lot of these systems, we just have 1 there, and it's just a simple system like that. It's quite handy. You can almost forget that we have the exponents multiplied by OH minus. And here we're going to divide by water. So the molar concentration of water as a liquid, it's kind of a funny thing to think about. How many moles per liter of water are there in a liter of water? Turns out that that's a very high number compared to what we're going to get with the H plus and OH minus. And it's simple enough to treat it as 1, which we can do for liquids or solids that we're in equilibrium with. If we reach an equilibrium with a liquid, then we can treat that concentration as 1 or unity. Maybe next time I'll derive that with you. For now, just note that that's an assumption. Or if we're doing an equilibrium reaction where we have some solubility chemistry. It's also an equilibrium reaction, dissolving versus precipitating. It's going to happen at some set rate. And if you have a solid, let's say concrete in a swimming pool, some of it will, tiny fraction of it will dissolve, and it will also have a reverse reaction. And we can treat the solid there as a concentration of 1. It kind of simplifies things. It does make mathematical sense, and it's just the way we do it. So this then becomes 10 to the minus 14th equals H plus concentration, molar concentration, times OH minus. If they're equal, which is what we call pH 7, then each of them are 10 to the minus 7, which is where we get pH 7. So we'll resume that part next time and go in more depth. And I'll elaborate on that. For the moment, what I want to end with is just getting your opinion. I kind of already know, but you can pretty much anonymously give me your feedback here on how you felt about the exam. In particular, your feelings of preparedness is helpful because, and first of all, I'm never going to bother to track your 8, 9 numbers back to who you are and what opinions you have. Not that they're that detailed here anyway, but any opinion is fine, is what I'm saying by that. But it does help me to get a feel for if you just felt completely blindsided, or maybe it's just you felt like you're prepared, but turns out that wasn't quite the case. Maybe the exam was too hard. There will be a couple of questions here. Give me some feedback of what you thought. Okay, so I'll go ahead and start it, because that should be everybody. So how'd you feel about the length of the exam? Okay, so very glad to see that. I was intending to make it on the shorter side and more on the manageable, or so more on the easier to manage than the more difficult to manage. So I'm glad about that. How well prepared did you feel? Normally I give the survey before I give the exams back. Okay. So apparently nobody aced it. I thought some people did pretty well. Perhaps they haven't seen their exam yet. Okay. So blue is definitely not where I hope, that tells me that there's at least a fair bit of you that I probably didn't help prepare you enough or guide you enough in your studies. So that's definitely not what I hope to see, but I certainly understand this. Talked about it already, but especially with the ppm conversions being awkward and challenging in an awkward sort of way. So what did you think about the difficulty overall? Okay. All right. Thank you. And we will see you. It'll be on Twitch on Thursday. Assuming no internet outages. Should be good this time.